Another big project I'm working on, which is extremely exciting, is we're working on this DARPA Robotics Challenge. And MIT is leading a team that I'm very proud of, a mostly student team that's competing in this ridiculously complicated challenge with humanoid robots. It need not be humanoid. We have a humanoid robot that's being sent into into a Hollywood set that's meant to look like a disaster response scenario. And it has to do all kinds of complicated things, like removing debris from a door, going through a door, climbing a ladder, getting into a car and driving a car, right? Walking across rough terrain, picking up a drill and cutting out a hole in the wall, picking up a fire hose and mating it with a connector. These are all individually extremely complicated challenges, and we have to now do it with our big complicated humanoid robot on game day. So it's actually been a fantastic challenge for us. It was an interesting time where we had made a lot of advances on the algorithms, both on the perception, the user interface design, and the algorithms for planning and control. And this competition has brought us together, a number of groups at MIT together, in order to bring those technologies together in ways that they hadn't, get students extremely passionate about working on one common goal, and we've really matured the technology at an incredible pace to address the challenge. It's been a lot of fun. One of the things I'm most proud of about our solution right now to the DARPA Robotics Challenge is the fact that the planning and control code that we use to power our Atlas robot is actually almost exactly the same code we use to power our unmanned aerial vehicles flying through the forest. There's a lot of really core technology that is general enough in terms of the way it thinks about dynamical systems to work in both. Because we're using the same code base on both projects, for instance, one of the things that's come out of it is now we have UAVs that are making contact and not being afraid to make contact. We have them perching on a wall, we have them grabbing trees and bouncing off trees, because the same planning and control infrastructure had to be adapted to make it work with the friction and mechanical contact problems in Atlas, and now the UAVs get to benefit. So one of the great stories in the DARPA challenge is the fact that the first trials, which happened in December of 2013, everybody said the humanoids were going to just embarrass themselves and fall down, and we should just be going in with wheeled robots. Why are people working on humanoids? In fact, that didn't happen. The humanoid robots were many of the top teams that won in the competition were using bipedal robots. The robots really showed the world that walking technology is at least good enough to do some meaningful work. But the thing that happened was all the robots moved very slowly, right? So anybody who watched the competition, I think, couldn't help but be impressed that the robots could accomplish the goal, but also couldn't help but be a little bored at how long it took to accomplish the goal. And part of that, honestly, was due to the rules. We were given 30 minutes to accomplish a relatively easy task and told that failure wasn't an option. We had one chance to do each task. So we had to move sort of conservatively. But what you're going to see in this upcoming challenge, I think, is that we're going to make our robot move a lot faster. Now, there's at least two ways that it's going to move faster. So the first way is that if you watched our robot in the December 2013, there was a lot of dead time. So the robot was actually just sitting there waiting for the human operator to tell it what to do next. Okay? We're getting rid of that quickly by putting more and more autonomy into the robot. It used to be that in order to pick up a drill, we had to have a lot of human interaction, where we would look at the plan the robot was proposing. We would say that's okay. We would let it go. Now we have enough faith in our system that we can basically just let the robot be autonomous most of the time. So a number of the tasks that happened in December 2013 with a lot of manual control, we can now do almost completely autonomously. And another aspect of speed that we're working on is just when the robot is moving, it was moving very slowly before. There's something that you can do with a robot which makes everything easier, which is if you're quasi-static. If it means that if you were to stop moving at any given time, you wouldn't fall over. You're basically a statue at all times, and you have stability because you never put your center of mass outside your support polygon. Okay? If you stay in that regime, life is slow, but you can get work done and be relatively robust. Now we're working on making things much more dynamic. That's my favorite part of the project. So you're going to see Atlas moving a lot faster. The next time you see our videos, you might even see him run.